Welcome everyone to AI on AI, the podcast where we unpack the frontiers of artificial intelligence. Today, we're diving deep into a fascinating and frankly mind-bending area, AI tackling formal mathematical reasoning. We're talking about machines not just calculating, but proving complex theorems with the rigor mathematicians demand. Our context today is the groundbreaking work on Deepseek-Prover-v2. To help us navigate this complex landscape, we have an incredible panel. We have our expert in deep learning architecture. Welcome.
Happy to be here, ready to talk models and training pipelines.
We also have our expert in formal methods. Great to have you.
Thanks, looking forward to discussing Lean 4 and the nuances of formal proof.
Joining us is our expert in AI strategy and business leadership. Welcome.
Pleasure to be here, excited to explore the business angle of automated reasoning.
We're thrilled to have our expert in reinforcement learning research.
Hi everyone, eager to delve into the RL magic behind these systems.
And our expert in LLM reasoning. Welcome.
Hello, ready to connect the dots between informal intuition and formal logic.
We also have our expert in AI ethics and reliability. Welcome.
Thank you. Important to consider the trust and responsibility aspects here.
And finally, our expert in computational mathematics practice. Great to have you join us.
Thanks for having me. Excited to discuss where these tools meet real-world problems.
So let's set the stage. Expert in formal methods. Why has getting AI to prove theorems formally been such a tough nut to crack, compared to, say, generating creative text or even solving math word problems informally?
That's a great starting point. Informal reasoning, like the kind humans often use or that standard LLMs excel at, relies on intuition, heuristics, maybe skipping a few steps. It's powerful, but it lacks absolute rigor. Formal proving, especially in systems like Lean 4, demands absolute precision. Every single step must be logically sound, verifiable, and syntactically perfect. There's no room for ambiguity.
Exactly. LLMs traditionally struggle with that level of sustained logical coherence and symbolic manipulation required by formal systems. They might guess patterns well, but constructing a complex, multi-step proof where every link in the chain is formally verified. That's historically been the Mount Everest of AI reasoning. Bridging that gap between high-level, intuitive understanding and the rigid syntax of formal logic is the core challenge.
Okay, so Deepseek-Prover-v2 takes a novel approach. Expert in deep learning architecture, can you walk us through the core innovation here? It involves something called subgoal decomposition.
Right? The key idea is elegantly simple, yet powerful. Instead of trying to generate the entire complex proof in one go, they leverage a very capable general LLM, Deepseek-v3, to first break the problem down. Think of it like a project manager outlining the major phases of a complex project before diving into the details.
And DeepSeek v3 does this by generating a high-level proof sketch, often using natural language chain of thought reasoning, and translating those steps into formal lean statements, but with sorry placeholders for the actual proof details. These placeholders essentially become the subgoals. It's a hierarchical approach, much like human mathematicians often work, breaking a big theorem into smaller, manageable lemmas.
So Deepseek-v3 acts like the strategist, outlining the attack plan
And then crucially, they use a smaller, more specialized 7B prover model to recursively tackle each of those subgoals, those sorry placeholders. This divide and conquer strategy is computationally smarter. You use the big brain DeepSeek v3 for the high-level strategy and a more focused workhorse, the 7B model for the detailed proof steps of the lemmas. Once all subgoals are proven, the complete formal proof for the original theorem can be assembled.
That leads us to the cold start process. It sounds like they're synthesizing the initial training data in a clever way. Expert in reinforcement learning research, can you elaborate?
Absolutely. This is where it gets really interesting for training. They take complex problems that the 7B model couldn't solve end-to-end initially, but could solve once broken down into subgoals by Deepseek-V3. They then stitch together the formal proofs for all the successfully solved subgoals to create a complete, verified formal proof for the original hard problem.
And here's the magic for the cold start. They pair this complete formal proof with the original high-level informal chain of thought reasoning generated by Deepseek-V3 that produced the subgoal decomposition. This creates high-quality training examples that explicitly show the connection, the translation, if you will, from informal mathematical intuition to rigorous formal proof structure. It's like giving the model a perfect worked example, showing both the thought process and the final answer.
An analogy might be like showing a chess student not just the winning game, but also the grandmaster's thought process for each key move sequence.
Precisely. It directly teaches the model how to bridge that informal-formal gap we talked about earlier. This synthetic data provides a crucial, cold start for training the larger, more powerful Deepseek-Prover-v2 model.
But the cold start isn't the end of the story. There's a significant reinforcement learning component. Expert in reinforcement learning research, how does RL polish this prover?
Right, the cold start provides a strong foundation, but RL fine-tuning takes it to the next level. They use an algorithm called GRPO, Group Relative Policy Optimization, which is quite efficient for reasoning tasks. Instead of a complex value function like in PPO, it samples multiple proof attempts for a problem and learns based on which ones succeed or fail.
So the reward is basically, did the proof verify in lean or not, binary?
Mostly, yes. A reward of 1 for a correct, verifiable proof, 0 otherwise. Simple, direct feedback. But they added a wrinkle, a consistency reward, especially early in training. This encourages the final formal proof structure to actually follow the subgoals laid out in the initial chain of thought sketch from Deepseek-V3.
This RL stage, starting from that synthesized cold start data, seems critical for strengthening the model's ability to truly connect the high-level plan with the low-level formal execution. It refines the reasoning pathways.
And they also employ curriculum learning. Those subgoals generated during the decomposition process aren't just used for solving the main problem, they're turned into new, easier training problems. This progressively builds the model's capability, starting with simpler lemmas and working up to the full theorem. It's like starting with arithmetic before tackling calculus.
Let's talk results. Expert in formal methods, Deepseek-Prover-v2 seems to be setting new state-of-the-art records on benchmarks like Mini F2F and Putnam Bench. How significant are these achievements?
They are quite significant in the neural theorem proving community, achieving nearly 89% on Mini F2F test, which contains Olympiad-level high school problems, is truly impressive. That surpasses previous approaches substantially. And solving 49 problems on Putnam Bench, these are challenging college-level competition problems, demonstrates strong generalization. They even introduced ProverBench with recent AIME problems, solving 6 out of 15 formally.
Expert in AI strategy, translate this for us. When a tech leader hears 89% on Mini F2F or solved 49 Putnam problems, what should a business leader take away? Does this mean AI is ready to replace mathematicians or quants?
Not replaced, not yet anyway, but it signifies a major leap in AI's capability for complex, logical reasoning and problem solving. Think about it, these systems are tackling problems that challenge very bright humans. The takeaway for business leaders is that AI is moving beyond pattern recognition and statistical correlation towards genuine, verifiable reasoning.
To add to that, the fact that these proofs are generated in lean means they are formally verified. There's no ambiguity about correctness, unlike a natural language explanation. This property is incredibly valuable for high-stakes applications.
The paper highlights 2 modes, chain of thought COTI and non-COTI expert in LLM reasoning. The COTI mode performs noticeably better, especially with more sampling. Why is that, and what does it tell us?
It strongly reinforces the power of step-by-step reasoning, even in formal domains. COTI explicitly prompts the model to break down the problem, articulate intermediate steps, the lemmas or subgoals we discussed, before generating the final proof. This structured approach seems to significantly improve success rates on complex problems. It's analogous to showing your work in math class. It helps organize thoughts and catch errors.
Interestingly, the paper notes that even in non-COTI mode, the larger 671B model sometimes inserts natural language comments resembling implicit reasoning steps. It suggests that these massive models might internalize reasoning structures even when not explicitly prompted, though the explicit COTI guidance clearly works better.
Now for a twist. Expert in computational mathematics practice, the paper mentions a surprise. The smaller 7B model sometimes solved Putnam problems the giant 671B model couldn't, using specific lean tactics like cardinal to nat. What's going on there?
It's fascinating. It suggests that sheer scale isn't everything. Sometimes a smaller model, perhaps through the quirks of its training or distillation process, might stumble upon or latch onto specific, effective techniques for certain problem types that the larger model overlooks. The 7B model seemed to develop a knack for problems involving finite cardinalities using those specific lean library functions.
It highlights the concept of skill discovery during training, particularly RL. The 7B model, possibly due to different training dynamics or data exposure during distillation from the 671B's rollouts, specialized in a way the bigger model didn't for this subset of problems. It's a good reminder that the path to capability isn't always just bigger equals better. Sometimes specific skills emerge unexpectedly.
Are you sure the 7B model didn't just get lucky? Finding a shortcut the 671B model was too sophisticated to consider.
Chuckles, well, luck in RL often means finding an effective niche strategy that gets rewarded. It found a useful pattern, using those cardinal functions, that worked for those specific problems. It might be less generalizable, but it was effective there. It points to the complexity of the training landscapes these models navigate.
Let's revisit the narrowing gap between informal and formal reasoning. Expert in LLM reasoning, Deepseek-V3 solved 8 AIME problems informally, while Prover-v2 solved 6 formally. Why is this comparison important?
It's a crucial indicator of progress. In formal reasoning, LLMs like DeepSeek v3 are becoming incredibly strong at grasping the essence of a mathematical problem and outlining a solution path. Prover v2 demonstrates that we're getting much better at translating that high-level understanding into a formally verified proof. The gap is shrinking. We're moving towards models that can both understand intuitively and prove rigorously.
Expert in AI strategy, what are the business implications of this shrinking gap?
It dramatically increases the potential for trustworthy AI in complex domains. If an AI can not only suggest a solution but also provide a verifiable proof of its correctness, that's a game changer for adoption in critical areas. Imagine AI assisting engineers in verifying chip designs or helping develop verifiably safe software control systems. It builds confidence and reduces risk, which are huge factors for business adoption.
Of course, it can't all be smooth sailing. Expert in AI ethics and reliability, what are the challenges and limitations we need to consider?
There are several. First, the sheer scale and cost of training models like the 671B parameter version are immense, limiting accessibility. Second, while formal verification is powerful, we need to ensure the problem formalization itself is correct. Did we translate the real-world requirement into the formal system accurately? Garbage in, garbage out still applies. Third, there's the verifier's dilemma: who verifies the verifier?
And from a business perspective, adoption is a major hurdle. You need experts who understand both the domain, math, engineering, and these formal methods tools like Lean. That talent is scarce. Demonstrating clear ROI beyond academic benchmarks is also key. It's great it can solve Putnam problems, but can it accelerate drug discovery simulation verification or find bugs in our financial trading algorithms? That connection needs to be made clearer for widespread investment.
I'd also offer a slightly contrarian view, building on Expert 3's point. While solving Olympiad or Putnam problems is impressive, are we potentially over-optimizing for these specific types of competitive mathematics? The kinds of proofs needed for verifying software correctness or complex system safety might have different characteristics. perhaps less intricate, but vastly larger and more repetitive.
That's a really important point. Let's look ahead. Expert in computational mathematics practice, what are the potential future applications if this line of research continues successfully?
The potential is enormous. We're seeing the building blocks for systems that could genuinely assist human mathematicians in research tackling conjectures that have stood for decades. In education, imagine personalized tutors that don't just check answers, but analyze the logical structure of a student's proof attempt.
The paper explicitly mentions scaling towards an alpha proof-like system, aiming for the IMO Grand Challenge. Achieving that would be a landmark moment, akin to AlphaGo for Go. It requires integrating this formal proving capability with perhaps even more sophisticated search and planning mechanisms.
For business, the long-term vision is AI as a trusted partner in innovation and quality assurance. Imagine feeding system specifications to an AI and getting back not just a design, but a proof that the design meets safety and functional requirements. Or using AI to rigorously validate complex financial models before deployment. It shifts AI from an assistant to a guarantor in some ways.
This has been an absolutely fascinating discussion. We've journeyed from the fundamental challenges of formal reasoning to the clever techniques like Subgoal decomposition and RL fine-tuning used by Deepseek-Prover-v2, explored its impressive benchmark performance, the surprising capabilities of smaller models, and pondered the significant implications for science, technology, and business. Key takeaways seem to be the power of combining informal intuition with formal rigor, the effectiveness of hierarchical decomposition and reinforcement learning, and the tangible progress being made in AI's ability to perform complex, verifiable reasoning. The gap between human-like mathematical thinking and machine proving is indeed narrowing. A huge thank you to our panel today. Our expert in deep learning architecture, expert in formal methods, expert in AI strategy and business leadership, expert in reinforcement learning research, expert in LLM reasoning, expert in AI ethics and reliability, and expert in computational mathematics practice. Your insights were invaluable. And thank you to our listeners for tuning into AI on AI. Join us next time as we continue to explore the cutting edge of artificial intelligence. Researchers introduced Deepseek-Prover-v2, a large language model for formal math proofs. This model aims to bridge informal human-like reasoning and strict formal verification. It operates using the Lean-4 proof assistant language. The core technique decomposes complex problems into simpler intermediate steps called subgoals. A general model, Deepseek-Version 3, creates initial proof plans and subgoals. These subgoals are then formalized into the Lean programming language. A smaller specialized prover model efficiently solves these individual subgoals. The solutions are combined to create a complete formal proof. This process generates high-quality initial training data called cold start data. Cold start data links informal reasoning steps with the final formal proof. The model is further improved using reinforcement learning techniques. Reinforcement learning uses feedback on whether generated proofs are correct. The team also used curriculum learning, gradually increasing problem difficulty. 2 proof generation modes were developed. One mode is faster but less detailed, called non-chain of thought. The other uses detailed step-by-step reasoning, called chain of thought. Chain of thought explains intermediate thinking before presenting the final proof. The main 671 billion parameter model achieves new state-of-the-art results. It reached nearly 89% success on the Mini-F2F benchmark test set. It also solved 49 challenging problems from the Putnam Bench college-level math dataset. The chain of thought mode significantly boosts performance on complex problems. The researchers introduced a new benchmark dataset called Prover-Bench. Prover-Bench includes 325 formalized math problems for evaluation. Deepseek-Prover-v2 solved 6 of 15 recent problems from a high school math competition. This competition is the American Invitational Mathematics Examination. An interesting finding involved the smaller 7 billion parameter model. This smaller model discovered unique proof techniques absent in the larger one. This work shows the gap between informal and formal reasoning in models is shrinking. Future plans include scaling this approach towards solving harder math problems.